Okay, in the name of God, let us get started. Welcome back to this next second class, which is about kinetic theory of gases. So this is what we have done in the first lectures, kind of giving a big picture of what we're going to be talking about. It's all about the interplay between experimental observations and theory, and then model building. We've seen that for the kinetic theory of gas, there are a set of observations and the theory that we would like to apply have been explained before, and the target where we want to reach somehow based on this oversimplified model of gas called ideal gas. We want to have predictions for pressure, molecular effusion, and other transport properties of gases. So today would like to start such that we dive in to the to start with the theoretical aspect. In particular, today I'm going to talk about a little bit about probability. Okay, and how that is going to be applied for the kinetic theory of gases. Okay. As mentioned before, again, one can imagine that there are a large number of molecules involved in a given gas. 1 gram of, for example, nitrogen or oxygen gas, something of the order of 10 to the 23. So it's really huge, and we don't want to apply classical mechanics to each and every one of these molecules, so we resort to an approach where we try to find or extract kind of so we try to extract average or some sort of collective behavior of this huge number of gases. And where this word average or collective comes in, that is where one may start to think about probability theory. Because based on probability theory, you can, if you have some sort of probability distribution, then one can compute averages. Okay? So, to begin with a recap for the definition of probability, what is it all about? I think it's good we go over those. So I write as follows. Probability is associated with events. Okay. Probability, if I say we make it PR, it's just a number. Okay. It's something which lies between 0 and 1. So it's a real number in 0 to 1. Okay. And to go a step further, I'm going to give an example of events, e.g. of events So we can clean that. One example is the flipping of a coin. If you have a coin, you flip it, that is an event. When you do that, for a normal coin, there are two outcomes. You get a head or a tail. Okay. So the flipping is an event. And the outcome of that event, for each outcome of the event, we associate a probability. Okay. So for example, the probability of getting a head after flipping a normal coin is going to be 1/2. The probability of getting a tail is also going to be 1/2. So this 1/2 is probabilities. You can see how those lies within this range of 0 to 1. Another example is tossing a die. Tossing a dice, the outcome is for a normal dice is 1 to 6, and for each outcome the probability is 1/6. Another example of an event is considering. So I'm going to put this in quotation marks. So considering or looking at a molecule. So this is also an event. One can look at a molecule to see what is the energy of the molecule, okay, or what is the speed of that molecule, and the probability of getting some particular value as energy is a number which has to lie between 0 and 1. Okay, and an example here for the extreme events, when the probability is 0, then the event is said to be impossible. And when the probability is 1, the event is said to be certain. So it's kind of 100% certainty that it's going to happen, right? So the extreme values. Okay. P probability of an event, if it is 0, implies that the event is going to be impossible. If we have probability of some event to be equal to 1, then that implies that the event is certain. Like for sure it's going to happen, right? So we'll move next. So revising what probability mean, the next thing is kind of to talk about something called distribution of probabilities. So probability distributions, right? I think this is best introduced using examples. Okay, so we can have a system on the consideration on one hand, and one can talk about probability distributions or probability distribution associated with that system. Okay. An example is one can consider a fair coin, a normal coin with two faces. So whenever you throw or flip a coin, there are two possible outcomes. It's going to be either a head or it's going to be a tail. So you can put that, say, on the horizontal axis to represent event, outcome, upon, for example, flipping a coin. We're considering a coin here. And then on the vertical axis, one can consider probabilities. So for a system, our system here is a coin. There are two possibilities. You either have a head or you're going to have a tail coming out. So the outcomes are like that. Oops, I'm going to correct this. So write a tail here. Okay. So the probability of getting a head for sure is 1/2. So I'm going to put a point here for a head. And the probability of getting a tail is also 1/2. And I'm going to put a point here for the tail, right? So one can see that the probabilities are the same for both cases, okay? So this is an example of a distribution. Like, depending on what the outcomes of events are for the system under consideration, if I know those probabilities for each possible outcome, then the whole thing is called kind of a probability distribution. I have a probability distribution at hand, and here is a flat. One can say, since they're the same, it is called a uniform or flat probability distribution. Okay. Another example is one can consider a coin. So if I draw a coin using a different color on the same graph, say if we have green for dice, so another system is dice. Okay. For dice, there are going to be how many outcomes? You're either going to have a 1 or a 2, a 3 when you throw a dice, a 4, a 5, or you're going to get a 6. So the outcomes are this. And the probability for each one of them is like the same. It's a value 1 divided by 6. So for outcome number 1, I can have a point here. For outcome number 2, it's going to be a point here. For number 3, the same thing. Number 4, number 5, number 6, right? So you can see it's these two examples for these two systems, which is a coin and a dice. For both of them, kind of the distribution, how does the probability change depending on the different possible outcomes, right? So they're flat, they're uniform, they're the same. Okay, so I have a flat probability distribution here. Okay, and one can think about different examples. So to come nearer to the case of kinetic theory of gas, which is our target, one can consider a molecule of gas. For example, molecule of an ideal gas, right? So this is a system, and the question one could ask is, for example, I can consider the velocity or the speed. I take a molecule from a gas at random and then try to see what the speed of that molecule is. For each value of the speed, there is going to be some probability, okay? And so this is going to be, if I call probability, actually it's going to be probability distribution, but let's say we have a P, which is a function of V. For each point under consideration, let's say V, let's say V0 plus dV. So here this point is V0, and then I consider an interval. So we're talking about an interval here. I can ask the question of what is the probability of getting V, which is the speed of the molecule, to be between, so we want probability V, which is velocity of gas, to be between a certain value V0 plus dV. Okay. I'm going to explain more. We're going to revise more why we talk about interval here. The reason is we're dealing with a continuous variable, let's say a continuous random variable here. And the continuous random variable in this example is the speed of the gas, so V, right? So we want to find the probability of the gas having velocity between V and, so it's actually between V0 and V0 plus dV. Okay, what is the probability that it's going to be there? So this is something we have to do. This is something we have to find out along as we go along in this lecture. For now, I'm just going to keep put a question mark here, but we're going to derive it, and we're going to find what that is. So actually, it's going to, as we're going to see, the probability distribution in this case is going to be a continuous, so this is continuous probability distribution. Continuous probability distribution. In this example here, for the case of a coin and the case of a dice, what we have was actually a discrete probability distribution. It is discrete because, as you can see, well, the events, the variable we're dealing with, the variable is what? The outcome of an event. The event is either, in this case of number one, in this example number one, we throw in a coins, and the outcome is going to be either a head or a tail. So that is discrete, right? A head or a tail. Or when you throw a dice, the outcome is going to be 1 or 2 or 3, 4, 5 or 6. Okay, so these are discrete possible values, and that's why the probability distribution is called discrete. Okay, but for the third example, the case of a molecule of a gas, okay, the values which the speed of a molecule of gas can take is actually continuous. So it's a real number, right? It is continuously distributed, right? It is 3, 3.5, 3.7865, I don't know, as you want. And that's why the kind of distribution coming out is called the continuous probability distribution. So this is a review. Let's move on. It's a review about probabilities, and I go to the next page. One of the properties, we should consider that, properties of probabilities. So I'm going to write this again. PR, if it's a probability, has to lie between 0 and 1. Okay. And the next thing is for a given variable, we're going to start with the discrete, let's call it random variable. We call it x. So the outcome, why do we call it random? It's actually what it is. It is random, right? So if you take the example of a coin, if you throw a coin, what you're going to get, a head or a tail, which one turns out, it's really random, right? It's if you have a normal coin, or a dice, if we throw a dice, it's like we're selecting a number, an integer between 1 and 6 randomly, right? So the outcome, if we represent the outcome as x, and we repeat the experiment a number of times, so we have different outcomes. For example, different possibilities depending on the system, right? So for a coin, there are 2 possibilities. So I is 1, 2. For example, 1 is going to be for the case when you have a tail, and 1 is going to be for the case when you have a head coming out, and 2 is going to be the case when you have a tail coming out, right? Another example, for the case of a dice, the possibilities there are 6 possibilities, so I goes from 1 to 6, right? So for each throw there are 6 possibilities. Now, so I'm just giving a name for these possible outcomes. The name is xi, right? So for a given discrete random variable xi with associated probability, the associated probability is going to be pi, right? So for example, the probability of getting xi to be 1, so head is 1/2, right? For the system of a coin, e.g. probability I equal to 1 for a coin is 1/2, right? So in this case, we can say, for example, xi x1 is a head, right? And so on. And for a dice, if you want probability for a system of a dice to have I equal to 3, so what is the probability of getting x3, right? x3 is going to be 3, so the outcome is 3. Probability of getting 3 is going to be 1 over 6, right? So for each event, there's going to be an associated probability, right? Okay, so this is my random variable xi. For each xi, I'm going to have a pi, right? And this is an example of discrete probability distributions, if we know what the pi's are. Well, one of the properties of probabilities is that if you sum over all the probabilities, that must be equal to 1 for a given system. For a given system. Okay, and this is something we have to check whenever we're dealing with probabilities. If we have summation over pi to be equal to 1, then it is a well-defined probability distribution, right? So having pi's is like you have the distribution of probabilities for the system, and what you can do is you can compute averages using that, right? So let's talk about averages. Next point. Once the probabilities pi are known, yeah, what we can do is that one can use those to compute averages. Okay. Now, what does it really mean to compute an average? I'm going to start with an example which we are very, I hope, which we are very familiar with. So the example is that given a set of numbers, so if I have a set of numbers x1 up to xn, right? So given this, what is the average? Okay, this is a well-defined question. Usually we compute the average as follows, to be x1 plus x2 plus xn. So all of them, we're going to sum them over and then divide by n, which is the number, right? And the assumption here is before talking about the assumption, I'm going to talk about, let us consider that x1, x2 up to xn are kind of random variables for a given system. So random variables that we call xi here. And this xi to x1 to xn represent the outcome of some events related to a given system, right? And if we consider the possibilities of getting each and every one of these random variables to be the same, then one can say that the probability distribution for that system is kind of uniform. And when it is uniform, actually, that is the assumption here. I have a set of numbers and I want to compute the average. We compute the average this way. x1 plus x2 up to plus xn divided by n. Actually, what we're doing is as follows. One can write this as 1 divided by n times x1 plus 1 divided by n times x2 plus, you keep doing that to the end, 1 divided by n times xn, right? And in a more compact way, one can write this as summation over I pi xi, right? So what are we really doing? For computing an average, we want to compute this average value of a given set of numbers, and for doing that, what do? We take the individual numbers, x1, x2 up to xn, but we multiply each individual number xi with its own associated probability pi, and then sum over, and that gives us an average, right? So we can take this on to make a more general definition of what an average is. So I can write this as the average value of x. X is a random variable. We write the average value this way between these brackets. So the average value of x, sometimes it's called the expectation value of x. Definition is you just have to do this summation, pi xi. So all you need to know is the probability distribution. And once the probability distribution is at hand, then one can easily compute the average of different things. This is an example, okay? Not just the average of x, one can compute the average of anything which depend on x. For example, x squared. Let me use a different color here. So to compute the average of x squared, all you need to do is to sum over pi xi squared. Or in general, if you want to compute the average of some function of x, that function of x, we call it f here. It can be anything that can be derived from the random variables x, and this is going to be summation over I pi times f on xi. Okay, so one can actually think about our system of ideal gas. For ideal gas, for the gas case, I mean, we're dealing with continuous probabilities, so it's going to be a bit different. And so I will talk a bit more about continuous random variables. Okay. For continuous random variables, in this case, let's say that this variable x is a continuous random variable, right? So an example is velocity of a gas, as we've mentioned several times. For example, this is velocity. So velocity take real number values, right? And the issue is that for a given system, let us think of a system which can have velocity. So for example, let us consider a molecule of a gas which can have velocity to range between 0 So it is not moving, to the case where, for example, the velocity is some number, I don't know, let's say some v max, right? So in between this, within this range, because velocity is a real number, right, there are infinite number of possibilities here. So in this range, there exists, let's say, infinite possible values for the velocity. So for this reason, one can think of the probability, let's say probability of having like a velocity to be equal to a particular number, let's say v0. If I choose randomly v0, probability of getting v0, it has to be really, it's not defined, because this is just one possibility out of infinite number of possibilities. So the answer is going to be one sort of hand wavy, 1 divided by infinity, or we'll say it's actually going to be 0. Okay, so in parentheses I'm going to write, say, 1 divided by infinity. It's not defined, but we take that to be 0. So we cannot talk about probability of gas molecule having a particular value v0. Okay? Instead of that, we consider a very small interval. So one can talk about the probability of having the velocity of gas to be between, so between v0 and v0 plus dv. So this is something which is more sensible. Like we consider another point here. So there is an interval, a very small interval here, dv. So this point is going to be v0 plus dv. Now we can talk about the probability of getting a molecule of gas to have velocity between v0 and v0 plus dv. Okay, and for such cases where we have continuous random variables, just like the way I have explained, what is actually happening is that we write the probability this way, like probability of getting v0 is translated or written in this manner, that it's going to be p of v0, some p of v0 times some p of v0 times dv. Okay, so probability is actually, so the left hand side is what we want. Okay, some sort of a measure of probability to have a gas with velocity value equal to v0. Okay, so this left hand side is probability. I'm going to, this is probability. It's somehow going to be equal to probability density times volume. Okay, so we can think about this interval to be a one-dimensional volume, right? So we have a volume here in the space of velocity. Okay, so the word volume is used in order to generalize it. We can have a two-dimensional case or a three-dimensional case, or four-dimensional case. It could be multidimensional. So one can talk about volumes in phase space. But here, to start simple, our space is velocity space, which is one-dimensional. So the volume is just dv. So actually, when we deal with continuous random variables, there is a probability, density, distribution, so to say, which is important. And once one have got that, then we can compute averages. We can do so many things. So one can consider the vertical axis here, for example, to be p function of v. Okay, so it could be, I don't know, depending on the system under consideration, you're going to have some curve, right? And actually what we're doing when we compute P times dV is that we're computing the area of this curve, area under this curve within the interval under consideration. So here is it, I'm considering an interval dv, and if there is a way, I'm going to mark this region. If you compute the area under the curve is the probability density distribution. So PV times dV is going to be an area, right? And this area is going to be the probability. So this is what you are measuring. It is the probability. Here you have, or maybe it's better to use a different color here. Let me see. Going to pick. So this is area is equal to probability. Okay, and this is probability density, or we can actually do that. Say this PV is probability density and the volume is dV, right? So the volume we're considering is here, dV, right, in one dimension. So this is now we're going to have probability density, and as before, for the cases of probabilities must always respect this equation that the sum of all the possible probabilities for the system under consideration, it has to be equal to 1, right? And therefore, if we integrate P function of V dV, we have to get that to be equal to 1. This is a property of probability. We've mentioned that before, that all the possible values for PR, they have to be between 0 and 1. And now when you sum them up, it has to equal to 1, right? And from here, PV is the probability density, probability distribution. Once we have probability distribution, so if we know what this function is, PV, then we can compute averages. And what we're going to do somehow later within this set of lectures is that we're going to find the probability distributions for ideal gas, and we're going to use that for kinetic theory of for the model we're going to construct and make predictions which can be checked with experiments. Okay, so coming back to the issue of computing averages, if I have a probability distribution, if a given probability distribution is known, let's say PV, then one can compute averages. For example, the average of X is going to be integration for the case of continuous variable. So you're going to compute X and then multiply it with Px. So it's like Xi times Pi for the case of discrete variables, which we have over here. But probability for the case of continuous variables is actually P of X dx, right? So we have this formula, which is similar to the one above for the case of discrete random variables. So this is for continuous random variables, and that one here is for discrete random variables, and you can compute the average of any function of the random variable. So for example, average of f of x is going to be integration of f of x times the probability. Probability is going to be px dx, right? So we now have a way of computing averages. Once we have probability distributions, then it's easy to compute what averages. Here is the average for a discrete random variable, and over here downstairs is the case for continuous random variable. I think that's it for today. I hope you enjoy it, and I hope this is going to be useful. I'm going to say goodbye. See you next time. Take care.